Assalamualaikum. Good morning. Today we will continue on noise pollution. I hope everybody aware that I have loaded the project last week. It work in pair, divided the work in 2 weeks. So every week you should have some progress. Let's let me prepare a report. Submit to the groups. So for today class, I'm using two books. The first one is environmental management, um, handbook of environmental engineering, advanced and less noise pollution control, both are available in PDF. So source of noise, this is well known, right? Appliances in home, at home, such as the mixer and the grinder, cause a cumulative sound of about 87 decibel. While the factories using single or multiple units should could cause sound above 98 decibel and above. Later we will do some calculation. Airplane has the highest sound among all, 150 decibel, which is why they are required to use the ear muff. There have been reported that high intensity, high frequency, and continuous factors of the workers. Yes, that is true. Some example later. It causes physical, psychological image, impair or specificity. So it affect the health. Last week, the A-weighted decibel scale begin at 0, similar as last week. This is from a different book, how they explain it. This represents the faintest sound that can be heard by human with very good hearing. The loudness of sound, that is how loud they seem to human, varies from person to person. So there is no precise definition of loudness. Based on many tests of large number of people, a sound level of 70 is twice as loud to the listener as level of 60 that last week calculated. The lawnmower, although both is 60 decibel, is it 60 decibel? 60 decibel. But if we have two lawnmower operating at the same time, because the calculation is based on logarithm, so total for two lawnmower is not 120 but 63. That's why 70 is considered loud. This is the threshold of hearing from 0 to 90 modified motorcycles. Physiology of hearing. Just for your information, you have this outer ear, middle ear, and inner ear. So outer ear is okay. This is implied injury. Here, ear canal, zonate depression of air, region. So since sounds transfer by vibration, so that's why the ear canal will enter our ear canal. This is theory. So the variation of air pressure that make up sound. So the function of ear canal is to have the sound wave included. This is biology. Effect of noise on production on health. As we go in detail, some of it is in influence, affect cardiovascular. This is what happened. Be exposed to noise, such in heart rate, pressure, slow active breathing, auditory health effect. Still using referring to environmental management book, page 404. So some of the auditory effect is acoustic trauma, so sudden hearing damage because gunshot was extremely loud noise, such as gunshot tinnitus, which is ringing or buzzing the ear, temporary hearing loss, if the exposure to high level of noise. It will recover because can be sometimes quite yes, permanent hearing loss. It will slow down is permanent threshold shift. Characteristic of noise. So noise induced hearing loss is a cognitive process. Both level of noise and exposure time over both history are important factor. So low frequency noise is less damaging compared to noise in mid frequency. In the initial stage, noise-induced hearing loss is most pronounced. It's 4,000 hertz, but it's spread over other frequency at noise level in exposure type increases. So workers in noisy environment who are also exposed to vibration, checking may experience greater hearing loss than those exposed to the same level of noise. But should the the detailed explanation is in the book, something to do with the organ in the ear, how the vibration influence those, refer to page 406. So how to measure the hearing loss? So to Hearing loss is measured as a threshold shift in decibel unit using an audio meter. The 0 dB threshold shift reading of the audiometer represent the average hearing loss threshold level of an average young adult with the disease-free ear. The PTS, as measured by audiometry, is the decibel level of sound of different frequency. They're just very audible to the individual. Uh, a positive threshold shift represents hearing loss, and a negative threshold shift means better than average hearing when compared with the standard. Okay. So several methods of calculating the percentage of hearing disability are in use. So America is using the formula by American Medical Association or American Academy of Otolaryngology. So this method, the average hearing threshold level at 500,000, 2,000, 3,000 should be calculated for each ear. Multiplying one should calculate the percentage of impairment for each ear. Okay. The detail in page 407. But yeah, our task is to, this is more fluid. Yeah, if you want to be more, how they calculate the measuring loss. Industrial noise. No environmental factor has caused so much confusion regarding its effect on workers' efficiency and workers' health as industrial noise. Noise industry originates from processes causing impact, vibration, or reciprocation movement, friction, and turbulence in air or gas streams. Noise emission standards have only an indirect control over the noise generated by a machine. The state maximum permissible sound level in workplace acceptable daytime and nighttime is level in solution. Okay. The maximum permissible sound level at workers here in the time of the not integrated into the device produced by any on machine but depend on the total noise simulator we will calculate. So because there's many tasks and then there's one worker might not working on the same task the whole day. So the noise exposure is different. So there are method and table required to calculate the exposure. So in the book, figure 15.3, the relationship between exposure and hearing loss. The y-axis is a percent population with hearing loss worse than 25 decibel. X-axis is the age and years of exposure. So by age 40, with exposure around 20 years, for 95 dB, how many population? It's around 25%. Actually, 15% population will have a hearing loss greater than 25 dB. That is the study. The measured noise in such case can be produced by a single machine or by a combination of many kind of machinery. Show figure 15.4-15.4a show the relationship between the level of noise. And figure 15b show the various path for the management of noise. Noise regulation. So OSHA set the noise exposure limit at an employee creation for environment of steady noise, mixed noise, and impact noise. And there you go, what is the impact noise, steady noise, mixed noise? For steady noise, it's constant decibel A-weighted level over a period of time, maximum period of 90 dBA. About the sound level emitted from a loud engine for an 8 hours day is prescribed with halving of exposure time for exposure 5 dBA increment. So this is the permissible steady level noise exposure. Table 1 present permitted exposure. Permitted exposure for various noise level. This is based on book uh, 3 in ELIT, Advanced Air and Noise Pollution Control. For mixed or varying level noise, the exposure may not exceed a daily noise dose dt of unity. Unity means 1, as expressed in equation 2. So dt equal to d1 over d1. So until the end of the day. So d1 or dn here is the actual duration of exposure at noise level n, and dn is the noise exposure limit from the table 1. So the n is coming from table 1. D1, D2 until the end. That one is based on the circumstance or the condition the workers will keep. How many hours exposed to that sound level. The impact noise are generated by machines such as drop hammer, punch presses. Exposure to such noise must not exceed a 440 decibel peak sound pressure level. The peak sound pressure level also determines the maximum number of impacts per day that an employee will be exposed to. As indicated in table 2, so this is the permissible impact noise exposure. So for 140 dBA, because it's just one of. So for 140, the impact must not exceed 100. Maximum is 100 impact per day. For 110 is 100,000. But this permissible impact is for the calculation of equation 2 or this equation 2. So the impact, you can also refer to table 15.3 in books environmental management. But this is focusing on ICE, internal combustion engine. So many type of source. So how long the exposure is. Oh, if an employee is exposed to both steady noise and impulsive noise throughout the day, the combined effect can be handled quite simply for predictive purposes. One needs to treat the ratio of the number of impact n at a given peak sound pressure level to the maximum number of impact allowed at that level and get discretion to the steady level calculation. Currently, there will be an example and exercise for you to try for you to do. Hearing conservation program must be implemented that will include at least an annual biometric test for employee exposed to those level related 85 dBA for an hour of whose noise dosage DT. This is referred to the question 2. Meet or exceed zero point 0.5. Example. A group of factory workers are subjected to the following sound removal daily. So this is the location. So each location, the group factory workers, for example, in Turkey, because it's around 85 dBA, they need to work in Turkey for how many hours? 9, 10, 11, 3 hours. Yeah, 3 hours. Then they move from 11 to 12 noon at the press room for an hour at 92 dBA. The last one is a turbine room. This is the highest one, 4 dBA for an hour. So in addition, they are exposed to 12. So beside this exposure, they are also exposed to 12 impulsive event from various sources that have a sound level of 150 decibel at peak. So impulsive sound means it's happening once, second, but it happened twice, 12 times throughout the day. The workers are outside for lunch from 12 noon till 1 p.m. So meaning they are not exposed to noise as high as this. Even if it's permissible for the worker to work in this environment. So from equation 2, the noise dosage from all event is, see this, remember the equation is T1 over T1 plus T2 over T2. So 1, T2, T3, that represent the event. Then the last one is the impulsive event. So 3 here equal to how long the exposure in hours? 16. So 16 here, you need to refer to table 1. It's at 85 dBA. The time method is 16 hours. So how to read this table? So dash mean, so 16 hours. For 89 dBA, it's 9 hours, 11 minutes, and so on. So for this case, 85 dBA, so it's a 16, 3 over 16. How about 92 dBA? So 92 dBA is 6 hours and 4 minutes. If you turn it to hours, it's 6.06 hours. This is only 1 hour. Okay. So for 94 dBA, it's 4 hour 36 minutes. So 36 minutes to convert it to hours. So in total, DT is 0.772. Therefore, the workers can work in this environment, but they should have their hearing checked periodically because their exposure is greater than 10.5. Okay, let's try the exercise one. The location is the same, but just uh, the sound level is different, exposure is different. Is it different? It's different. So how to do this? You need to refer to table 1. Identify first. At 90 dB, what is the time per minute? So in this case, 90 dB is 8 hours. So you got 8 hours. How about 96? 96 is 3 hours 29 minutes. So 3 hours 29 minutes convert to hours. Do the same for until turbine room 94, then identify the impact for 120. So if it's 120, the permissible impact loss of pressure is around 10,000. So meaning it's 10 divided by 10,000. So once you identify the limit, then you just plug into the equation 2 to identify the T. 1 minute. I just want to do the calculator. Question so far? I don't have the answer, but just follow the example, how to calculate it. Measurement of noise. Still referring the advanced air and noise measurement control. Of noise. Of noise. What is page 410? 48. Oh. Temporal distribution is particularly useful for determining and expressing noise exposure in urban areas. Noise level fluctuate considerably in the course of a 24 hours day. One way of evaluating temporal characteristic of noise is by expressing noise level and represented by Lx, where X is the maximum percent of the time that the specified dBA level may be exceeded. Thus, L1 may be read as a noise level that is exceeded only 1% of the time. A very high noise level indeed. On the other hand, 95, L95, and regarded as background noise that is exceeded 25%, while FL50 corresponds to a temporal median noise level. LX for a particular community may be determined either by a sufficiently advanced sound level meter or direct acquisition and manipulation with a digital computer. Another way of expressing the temporal behavior of community noise is by equivalent noise sound level and EQ, short equation 3. This is a single number noise descriptor whose mathematical definition for a time interval T1 to T2 is equation 3, where T is the time period A weighted sound level. Pref is the reference root mean square sound pressure of. So the value for Pref is constant 2 to the power of 10 to negative 5 n over n square. So another method is LDN is yet another descriptor of community noise and is called the day-night average sound level measured application 4. Here the data are analyzed in the case of L equivalent except that 10 dBA penalty is applied to nighttime level with night being defined as the period between 10 p.m. to 7 a.m. The minimum sampling period for the evaluation of LDN is 24 hours. The formula used is equation 4. So in this case, LD is LEQ during daytime hours, 7 a.m. to 10 p.m. LN is the LEQ for nighttime hours, 10 p.m. to 7 p.m. The LDN obtained from the above equation may be corrected for seasonal background noise level and the presence of pure tone or impulses. For steady level noise survey measurement are performed with an A-weighted sound level meter utilizing the slow response setting and comparison estimate with table 1 to check for compliance or violation. The noise is not at so when it's not at constant level of an employee task take him or her from one area to another of different sound level, the daily noise dose can be limited from equation 2. Remember the DT? Describe the method to calculate the noise exposure. So to calculate the noise exposure, the easiest way is using noise dosimeter. It's a handheld equipment. If you don't have the dosimeter, then also calculate the noise exposure using the sound level meter and a stopwatch. So with these two, we can relate, we can calculate the noise exposure using equation 2. Because equation 2 is d equal to d1 over t1 plus d. So t refer to the exposure, how long t is the permissible limit of table 1. Noise control, general information. There are essentially three approaches to noise reduction and control. The first of these is to control noise at the source. One version of the source control team is operation-oriented. In that, effective noise control may be achieved by introducing alternative method of performing an operation and modification or alteration the noise path between the source and the receiver. So this is the three essential approach to reduce the noise control at source. The next one is the alternative method performing the same operation or modify or alter the noise path between the source and the receiver. So meaning barrier. Noise control can be achieved by careful consideration of noise control during the design of new product. Thus, adequate muffler, control intake and exhaust noise, and absorptive enclosure and design modification to engine can result in quite to industrial operation and automobile. Similar consideration applied to jet aircraft. Noisy sources can be housed in an enclosures whose performance depend on the type of enclosure used. The source noise control can also be taken as a retrofit measure, but this may be more expensive and could result in performance compromises. In many machines, there can be found metal to metal contact. This may be replaced with the softer material for machining and choose between the metal part. One version of source control team is operation oriented. In that effectiveness control can be achieved by producing a limited performing and operation. Example, one can see that noisy operation that might incur 10 decibel penalty in the LDN metric, whereas the same operation performed during the day would not. Penalty means it's F. Let's say LDN is around 50, so the penalty is with the penalty is quite. So this approach is being followed by major airline normally scheduled flight by the getting take off and landing procedure major airport. So when the desired amount of noise reduction cannot always be achieved by good acoustic design at the noise source, the next best solution is the modification or alteration of the noise path between the source and the receiver. Rerouting or relocating noise source is an example of application best applied in the planning stage of the highway and airport. In many plan, one way to the third method is just alter the path or by the path of the noise. So disperse noisy quiet equipment is dispersed throughout the plan. It will be found feasible to concentrate the noise specialized in the area where effective noise control can be introduced. So this is one way uh, to combine or collect the noise equipment in one location. and implement the effective noise control there. Another method of path modification is to interpose barriers between the source and receiver, such as shielding. Is useful in attenuating highway noise level. This is the one that we discussed last week. The barrier near the highway. Okay, good. The source control step coupled with path modification should result in the adequate noise reduction, whereby the individual is subjected to no more than an acceptable noise level. However, this is not always possible, as in the case of factories and workshop, where noise level may be high in spite of adequate control. In such cases, the close approach to control noise is the personal protection for control at the receiver. Either the individual exposure to noise level must be limited to dosage level by limiting time and dosage level of further protection being afforded through the edit of devices like earplug, headphone, earmuff. In the case of residential or community noise control, replacement window or door with better fittings in will be needed. Right. So the physics of sound. This is technical. Technical theme of advanced and noise pollution control. Sound is a disturbance that propagates through an elastic medium, air, water, etc. At the speed characteristic of that medium, noise and its control can encompass a wide range of mediums such as underwater noise from ocean traffic or unwanted vibration in mechanical structures. When a sound source in air vibrates, causes the air to oscillate, which in turn produce extremely small changes in pressure of the surrounding air. The pressure waves spread out like ripple on a pond when a storm is struck. It's a wave. Except that sound wave fill the whole volume of air as confined to surface. One. So speed of sound in the frequency sound propagated with velocity c defined by equation 1. This is equation 1, chapter 13. C equal to 20.05 square root Tk. Tk is the temperature. So these two would be the same thing, but in different units. This is in meter per second. This is for the second, for feet per second. You need to convert the temperature to Rankine. A simpler formula for the velocity of sound in air is sufficiently accurate at normal temperature 0 to 30 degrees C is equal to 331 plus 0.60 C. So C here is, sorry, temperature here in degree C, centigrade. Example, determine the speed of sound at 20 degrees C, 68 degrees Fahrenheit. In both metric and English unit, Kelvin is to convert 20 degrees to Kelvin, 68 degree Fahrenheit to Rankine, and calculate using equation 1. So the speed of sound is 343 meter per second, or 1,125 feet per second. With sound pressure, the sound wave produce changes in the density of the medium. As they travel through it, these changes in air density causes pressure fluctuation around the ambient static pressure. If a particle oscillates in a harmonic mode, sinusoidally varying with time, sound pressure will also change harmonically and cause a pure tone. For a pure tone, the sound pressure P can be described as P equal to, this is equation 3, equal to A sin omega t, equal to 15 to pi. F t Pascal, F is the frequency, t is time in second, omega angular frequency in radian per second. So omega equal to 2 pi f. So A is the amplitude in Pascal. So figure 1 shows a pure tone oscillation. Although pure tone do not often exist in nature, even musical instruments do not produce the pure tone. Frequency. The frequency of a sound indicates the number of cycles performed in 1 second. So F equal to 1 over T, where T is a period of one full cycle. The unit for frequency is the hertz. So this is the unit conversion for hertz. 1 hertz equal to 1 second per second equal to 1 CPS. Wavelength is equal to the distance the oscillation have propagated in the time period. Uh, so example to determine the wavelength of 125 hertz and 8,000 hertz tone at 20 degrees C in both metric and English unit. For 125 hertz, this is the calculation. So C is referred to speed of sound. So for this related to example 1. So 343 is coming from 343 per second. 125 per second. So the wavelength 125 hertz is 2.74 meter. The another one is 8,000 hertz. So 8,000 hertz. The wavelength is 4.3 cm. 0.0043 meter. It is small a bit. At higher frequency. Exercise. You can try this one using equation. Uh, equation 6. Determine the wavelength of 150 hertz and 7,000 hertz at 20 on 60 So how to calculate? It's 343 divided by 150. That one is for the 150. This is a metric unit. Another one is 343 divided by 7 times. You get the name. The sound pressure level. The sound pressure that are normally measured with a sound level meter cover an extremely large range. In order to handle in a simple fashion such as a large measurement range, a logarithmic measurement scale is used. Other benefits to using such a scale because the human response to sensation correspond to a logarithmic intensity scale rather than to a linear scale. So the sound pressure level that is at logarithmic ratio, LP, defined as equation 8, where P RMS is the sound pressure of interest in Pascal, or P RMS. I didn't cover that. P RMS is available. So in book, you can refer P RMS in question 7, page 428. P reference, this one is same value, 20 micropascal. Then the unit for sound pressure level is PN, and P is decibel dB. Example, determine the sound pressure level for sound pressure of P equal to 1 Pascal and P equal to 1 ATM. So solution reference is 20 megapascal. It's the limit of hearing. So LP equal to 20 log 1 over 20. This is the LP. This is LP. So P RMS, the unit is in Pascal. So 20 log 10 to the power of 5 divided by 2 equal to 24 dB. So for LP at 1 ATM, so here, so 1 ATM equal to 1.013 times 10 to the power of 5 in Pascal. It's around 194 dB. Exercise, okay. 1 minute. Equation 8. Two value for LP, 5 PA and 5 ATM. Done. To calculate LP equal to 10, 20, equal to 20 log P5, okay, 5 PRMS. The first one, 5 divided by 20 times 10 to the power of -5. Dapat dapat. So 20 log dalam 10 pasal 5 bagi 5 times 10 to the power of 5 divided by 2. Cuba. Loudness. So a young unspoiled ear can hear pure tone if they have sound pressure level as a function of frequency as illustrated in the lowest curve in figure 2. Oh. A 20 Hertz tone must have a sound pressure level about 70 decibel higher than a tone at 1000 Hertz. In order for a person just to hear the tone, the curve also indicated the loudness. The subjective interpretation of the magnitude of sound for pure tone. So for example, figure 2, the threshold hearing of 1000 Hertz here is about 4 decibel. About 4 decibel. It can also be seen in figure 2 that the ear is more sensitive to sound in the frequency in range of 300 and 6000. 300 and 6000. The sensitivity dropped at lower and higher frequency. Yes, correct. The family of curve in figure 2 indicate the sound level, pressure level, tone must have in order to be as loud as 1000 Hertz. With the sound pressure level as indicated on the curve, 20 Hertz tone must have a sound pressure level about 70 decibel higher than a tone at 1000 Hertz in order to for a person just to hear the tone. So 20 Hertz is here. uh, 1000 hertz, 20 hertz. Awesome. So 70, at least 70. The curve also indicated the loudness, the subjective interpretation of the sound of sound. For pure tone, the unit. Okay. So this is the unit describing loudness are called phone. By definition, the phone is equal to the sound pressure level in reference to 20 micropascal of an equally loud 1000 hertz tone. So what does it mean is it's actually normalized to this reference. The pen will occur when the loudness exceeds 120 phones. An approximate measurement of the sound loudness of a pure tone can be made by using a sound level meter with a reading network. So most sound level meter are equipped with reading network A, B, and C. Let's cover this. So we have weighted for A, B, sorry, A and C. B is actually the without no weighted. It's a dB, dB or dBz. So for figure 3, so initially the intent was that for loudness in the 30 to 60 phone range, the A weighting should be used. This is rule of thumb, how to use figure 3 here. Whereas in the 60 to 90 phone range, the B weighting applies. And loudness above 90 phone, the C weighting is the most appropriate. Indo sound. So the acoustical environment in a room depends greatly on the size, shape, and other properties of the confining wall, floor, and ceiling. Before examining how the properties of the room affect the sound field, it is pertinent to examine a simpler situation. What happens when a sound source such as a pistol is fired out of the door in the absence of any nearby reflecting surface? As seen in figure 4, sound wave arrive at time t. So t is equal to r over c. R is the distance, c is the speed of sound. If there is a large wall or building at the distance near the firing position, near at the source, the receiver will hear a different sound. The first sound will be from the direct arrival, which is R1. The second one is the wave reflected over the surface wall or building. This is the R2. So human ear is able to recognize individual sound because they are separated by a time period of 50 milliseconds. If the time difference between the direct sound and the reflected sound is greater, an echo will be heard. If the time difference is less, only one modified track will be. But this is the useful. Those who do absorbent forum. So what they do, they need to reduce the time difference low, lower than 50 milliseconds. Otherwise, it will become an echo. Okay, example 4 in the book is same here. Determine the time receiver will hear a pistol shot when the distance between the pistol and the receiver is 200 meters. There is a building behind the pistol 40 meters away. Make the calculation for the two temperature condition. So C equal to 20.5 square root TK. This is the first equation, equation 1. In chapter 13, so C is 325 meters per second. Why you need to calculate? Because temperature influence the speed of sound. So at negative 10 degrees C, the speed of sound is lesser. Yeah, lower. Still at 25 meters. Then you calculate the T1, which is the direct. This is the receiver and the source and the receiver. The gap is 200 meters. So 200 divided by 325. The other one is because the building is behind the source. So for T2 is equal to 280. The first one is a 200 distance, and the second one is the reflection. 40 going to the wall, reflected back 40 meters plus the 200 meters. This is not like this is in figure 5. If you make them here, the side. This is reflected in the back. Yeah, is the same thing for 25 degrees. Let us see, then using equation 13 and 14. We calculate the T. So you notice the reflected sound wave is weaker than the direct sound wave. For two reasons, it will have traveled farther from the direct sound wave, which reduce the sound intensity, and some of the sound is lost in the process of the reflection. Okay. So interesting. Calculate this. 5 minutes. 5 minutes. 3 minutes. 3 minutes. So what you need to do, calculate C first. Equation 1. Find equation 1. Actually, so C is 20.05 square root of 273 Kelvin. Then you get the C. For T1 is 200. T1 is 200 divided by C. T2 is 280 divided by C. No, not 300 divided by C. For T2 is 65, 130, 430. So 430 divided by C. You get the T for get the distance for 0 degrees. For -5, you need to recalculate. C. 273 Kelvin divided by -5. Sign build up and sign decay. Okay. The changes in the sound field in an enclosed space when a continuous sound source is turned on and off, as shown in figure 6. In the first half of figure 6, yeah, every step up results from the arrival of a new reflection. Expressed another way, every step up It's on to the contribution from one of the mirror images. The farther away the mirror images, the later the contribution arrives. The individual step on the curve gradually becomes smaller and smaller because the mirror image lies farther and farther away. And the density of the sound wave get reduced at each reflection. A stationary or steady state situation represented by the horizontal portion of the curve in figure 6 is rapidly reached. The equation used to determine the acoustical properties are usually developed according to statistical techniques. Thus, several equations exist, each differing slightly as a result of the different statistical assumption made. However, all equations are based on the energy balance that will always exist. So energy balance is added energy minus absorbed energy equal to the change in energy represented by equation 16. W is the emitted sound power in watt. T is energy density. C is speed of sound. V is the room volume. Alpha is the absorption coefficient defined as the percentage of impinging energy absorbed on any given wall element of area S. Statistical technique must be applied to the middle term of the above equation that expresses the amount of energy absorbed per unit time. Let's say assume that any time the sound field is diffuse, the energy intensity is everywhere equal. Then during sound build up and decay, the solution to equation 16 is as follows. So sine build up equal to D naught 1 minus exponent. Okay, this is equation 17, equation 18, where D naught represent the energy density once equilibrium is reached, and A is the total absorption in the room equal to sigma alpha n Sn during the stationary equilibrium period. D naught. Reverberation time. The reverberation time T in a room is defined as the time that the sound pressure level to decrease to a value 60 decibel below its original value. So Sabin developed this definition and derived the following formula based on the preceding equations. T equal to 0.163 V volume over A plus 4 MV. So A is the has the unit of meter square Sabin. If the unit for S is the meter square, S is wait, check it. Definition. Yes. Just tell you see, S is available in one of the example. Yeah. Hello. Square meter. S is the square meter of absorptive material. Square meter of absorptive material. Used to. So this is equation 20. Then equation 21 to calculate the A. So A equal to alpha S. Alpha absorption coefficient. S is the square meter absorptive material, the area of the absorptive material. So reverberation is defined as time taken for the sound pressure level to decrease to value 60 decibel below its original value. So let's say it's 60. So we decrease to 60, it will become optimum reverberation time. From an examination of the reverberation time formula, can be seen that the total absorption in a room can be calculated from measured reverberation time. Optimum value exists for the reverberation time for various functional spaces. So for 100 meter cube for the lecture hall, the reverberation time in second is 0.05 to 0.65 second if the room is 100 meter cube. Same location, same value. For a 100,000 meter cube very big hall, the reverberation time is 1.1 second. Opera house, some churches. Energy density. It is important to recognize, however, that changing the reverberation time also affect energy density. The energy density in a room away from the individual sound source. Where the sound field is more likely to be diffused is directly proportional to the reverberation time. So D naught equal to 4W over CA and T equal to 0.16 V over A, so mean M equal to 0. The equation representing the relationship can be determined to be D naught equal to WT over 13.6 V, where C is taken as 340 meter per second. So C here is 360 meter per second for this equation. Yeah. Actually, C you can calculate the equation one. One, that's equation one. So this formula, equation 24, show that energy density in the room can only be reduced or the noise rejection is achieved either by reducing the sound power emitted to the room, which is reducing the W, or by reduction of the reverberation time the last being equivalent to an increase in the total absorption. Relationship between direct and reflected sound. It was determined that the energy state in the steady state station was question 19. Question 19. Close to the sound source, however, the energy density will be larger than D naught because of the contribution D from the sound source. Assuming the sound source radiate evenly in all directions, then D question 25, the ratio of D to D naught become question 26. As long as the ratio is greater than 1, we are in the direct sound hell, which means that DD is dominant domain, R square more or less than, or equal to A over 16 by R square. So, so this distance R can be used to determine how far away from a machine an operator must be in order to achieve a noise reduction in a room solely through the use of absorption materials. The total energy density in a room is given by equation 28. The sound pressure level SPL reference to 20 micropascal can be determined by accepting equation 28 into equation 11. So equation 11 refer to sound energy density, page 462. D equal to PMS, P square MS divided by rho or density of A multiply with speed of sound C square. Okay. And then utilizing equation 8, which is the sound pressure level, we get equation 29 SPL equal to PWL plus expression where PWL equal to equation 9. Equation 9. So equation 9 refer to sound power level LW, sound power level. SPL is sound pressure level. Example, okay. Determine the distance r for which the direct energy density is the main contributor in two different rooms. The first room with volume 300 meter cube, reverberation time 1 second. The second room is 20,000 meter cube, reverberation time is 2.5 seconds. So for the first one, 0.16, that with 300 meter cube, divide by T, the reverberation, equal to 48 meters per second. Then with equation 27, assuming the dd over d naught is more than 1, so we can use equation 27, which is 48 divided by 4 pi 16 pi. Equal to 0.95 meter. So R is less than 1 meter. For the room 2, it's around 1280 meters square second. And the distance R is less than 5 meters. To the exercise, short break, 10 minutes. You do this one first. So how to calculate? You need to calculate A first. Then using question 27. Some mistake with the question 27. It is without R square. So question 27 should be R square less than 10 over 16 pi. Noise reduction. Page 473. absorptive material, a reduction of the sound pressure level in room can often be efficiently accomplished by reducing the sound power emitted by the sound source. By reducing the emitted sound power, both the direct and the reflected sound will be reduced. However, it is often not appropriate to modify the sound source because modification may have adverse effects, such as reduced efficiency interference with the access to the machine. So in this section, we will consider how much noise reduction can be achieved by the use of absorptive materials. So let us look at example. An existing room has a total absorption of A naught. If S square meter of absorbed material is installed with an absorption coefficient alpha, then the total absorption after the installation will be A equal to A naught plus alpha S. So this equation is similar to the introduction of Sabin and the reverberation time. She's talking about this material, which is directly related to actually the A equal to question 21, A equal to alpha n S n, summation of alpha n S n. So if only the surface exposed to the incident sound determine the absorption. So if the new material covers any of the older material, A equal to so meaning if you have a layer of material, the older one you just retrofit the new one on top of the old one. So A equal to A naught plus S alpha minus alpha 0 alpha naught. The alpha naught is the absorption coefficient for the wall that will be covered with the absorptive treatment from equation 19. Equation 19. The energy density of the reflected sound will be reduced by following the equation 35, 10 log A over A naught dB. This is sine of delta R. So this one is for the new material. If the new material is place or install on top of all the material using equation 34. The energy density affected sound will be reduced by this equation. Determine the noise reduction of the detected sound that can be obtained in 20 times 25 times 35 meter cube space, where the reverberation time is 4 seconds and the existing ceiling material having an absorption coefficient of 0.25 is exchanged with the material having an absorption coefficient of 0.9. So first volume is 1,500 meter cube. Calculate for T 1.16. This is P divided by A naught. So at T equal to reverberation time of 4 seconds, A naught equal to 700 meters squared. Sabin A equal to A naught plus S in bracket alpha minus alpha naught. K A equal to 700 plus 25 on Q. Then A equals to 1.70 meters squared per second. So the reaction is 10 log 1.70 divided by 700. This is initial. This is after installing the material, new material. So we get a reduction of noise 2.6 dB. The best description in the book. Since noise is a combination of direct and reflected signal, the noise reduction that can be achieved is highly dependent on the initial amount of absorption in the space. In most practical installation, it will not be possible to achieve more than 5 to 10 dB noise reduction. A 10 dB reduction is equivalent to approximately half of the sound loudness rated subjectively by placing adsorptive material on room surfaces. The direct sound will not be reduced. Therefore, machine operators are allocated a few feet from the noisy machine will receive little benefit. However, the contribution to the noise pressure from listening machine will be reduced. All right, exercise appeal. Determine noise reduction for 10, 25, 25. So you need to calculate the volume. After that, calculate the A naught using reverberation time equation. Then calculate the new A, calculate the reduction factors. You try this 3 minutes. So to calculate this, V is 10 times 25 times 25. Then T is 0.16 times V that we calculated, divided by A naught. So reverberation time is T equal to 1. So we arrange the equation. So find A. A is equal to 0.16 times V divided by 1, T. Then you get the A naught. So using the value from A naught, you calculate the A equal to A naught plus S. S is the yes, 25 times 20. So A is equal to 25 times 25. And then alpha minus alpha naught. Alpha in this case is same 0.9 minus 0.25. Then you get the new A. So using with the new A, you calculate the noise reduction using 10 log A over A naught. You get delta equal to the noise reduction dB. The acoustic of a room are not affected by whether the sound energy is absorbed by a real or an imaginary surface. In this respect, an open window is a very effective sound absorber because it acts as a sink for all of the arriving sound energy. For real surfaces, the sound energy can either be converted to heat or transmitted as sound wave in the building structure. Sound absorbing material can, on the basis of the physical process involved, be separated into two main groups: the porous absorber and the resonant absorber. So for porous absorber, a complicated structure often manufactured from glass or mineral fiber pressed into board, held together by suitable adhesive. In general, although the acoustic properties of this material depend on a particle within the material being set into motion when a sound wave strikes the material. Furthermore, this motion is assisted by viscous forces in the surface of the fiber, result in part of the sound energy being transformed into heat. The porosity of the material is of great importance. If the porosity is low, then the sound wave will have difficulty penetrating the material, and most of the sound will be reflected from the surface. If the porosity is large, the sound wave will easily penetrate the material, and the reflection from the surface will be very small. Then we have a substantial absorption will be obtained only if the sound wave that penetrate into the material is reduced to a great extent. If the material, one valid generalization about porous absorber is that the first maximum of absorption of the test of the porous material equal 1/4 of the wavelength of the incident sound. So that is equal to wavelength over 4. So that is that how thick the material will be. So there are many factors that influence it, but one way to do it is by identifying the wavelength first. To identify the wavelength, you need using equation 6. So wavelength equal to CT equal to C over F. T here is not the temperature, it's a period. So F is frequency. So lambda equal to C over of a frequency. So once you get the value, so D equal to lambda divided by 4. So that is the maximum absorption. The thicker, better. Yeah. Figure 13 shows how the absorption coefficient theoretically should change. The thickness is changed. The first maximum on the curve should occur at the frequency having a wavelength equivalent to 4 times the thickness of the material. However, remember that the complexity of this porous material requires that one should only use the technique in experimentally. So we have frequency from 5 to 10,000. So figure 13 shows how the absorption coefficient theoretically uh, should change when the thickness is changed. The first maximum on the curve should occur at a frequency having a wavelength equivalent to 4 times the thickness of the material. However, remember that the complexity of this porous material requires that one should only use the trajectories obtained experimentally. If the absorption material is covered with thin plastic film, prevent contamination or spilling, then the absorption coefficient will change. The greatest change will take place at high frequency. The least change will occur when the film is not degraded. 50 micrometer or 1 to 2 millimeter. So for frequency, how much? 1,000, 5, maybe 5. So the absorption coefficient 2.5 thickness is around 0.3. 0.3. Then it's increasing. So the absorption coefficient here refer to the alpha. You see the calculation for A at the end, S multiplied with alpha minus alpha naught. So when we change the material, the thickness might change. So from the thickness, we can calculate, determine the new absorption coefficient based on this figure 13. Additional information. Eh, tak boleh. Four 76. So that is the porous absorber. The second one is the resonant absorber. Wait a minute. Ah, so resonant absorber can be thought to consist of a simple mechanical system containing a mass M and stiffness S. Each resonant absorber will thus possess a frequency at which sound energy being absorbed. The formula for the resonant frequency of such a system is F naught equal to 1 over 2 pi square root S over M. S is the stiffness and M is the mass. So one of the we have several example membrane absorber. We have Helmholtz resonator. So a membrane absorber consists of an impermeable plate placed at a distance from a wall in the cavity within the plate. Act as a spring with the characteristic stiffness. The resonant frequency for such a system is F naught equal to 600 divided by square root MD. M is the weight of the front plate, D is the depth of the cavity. The above formula does not consider stiffness of the front plate itself, but must be included if it is significant. Another one is a Helmholtz resonator. This is under resonance. There are two types of loss reduction, absorptive material. Under absorptive material, have porous absorber, then we have resonant absorber. So under resonant absorber, there are three types in the book. The first two is membrane absorber and the Helmholtz resonator. The Helmholtz resonator is an enclosed space with stiff wall. Helmholtz resonator, that one, if I'm not mistaken, is Dr. Asron, which is using a Helmholtz resonator yes, of course, um, to absorb the sound, the vibration, the sound, yes. But beside absorption, we transform the vibration energy into electricity. So that one is we do it in our centralized econ facility. So a Helmholtz resonator is an enclosed space with stiff wall in only a single opening room. We call a throat. Such resonator can be represented by a simple mechanical system consisting of a oscillating mass M plug of A in the throat resisted by a spring with the stiffness S. So the Helmholtz resonator, like any mechanical system, have a resonant frequency determined by F naught equal to C over 2 pi square root S over N over V. Question 29. Okay, interesting. Figure for membrane absorber. Figure 14. Do not move. But I already covered the part that you need for the report last week. Is sufficient. Yes. Can also apply what we learned within class, much more technical, especially when choosing the objective, so the method to prevent, to minimize the noise pollution. By next week, we shall discuss soil erosion for 2 weeks. I believe that is all for noise pollution. It's not much. You can just email us the problem or second as well.